as a thing can apply to other things we do in decentralized networks. So who am I? Hi, I'm Magic. I'm a co-founder of this company called Curious Storage Inc., which builds software for people providing services to decentralized networks. And previously I worked on this project that's IPFS and then later on that transitioned into work on Filecoin, which is this couple exabyte decentralized storage network storing real data for real companies. They also like doing weird hardware. But yeah, so that's me. I'm going to start by talking about what it is that decentralized networks try to achieve, just very briefly, and like in general, what like all of this decentralization is about. Then I would jump into kind of three broad topics of what I think confidential compute can apply to, and then kind of about the runtime components that will be really convenient to have for us. So yeah, the main thing in decentralized networks is really kind of trying to remove the mapping of I want to do something with someone. It should be just I want to do something and the software figures out with who, or like just kind of removing all of the trust and like specific contract mappings and just doing the thing. So retrievals should be able to happen just with other computers on the internet, and storage should happen with other computers on the internet, and kind of same with compute. Obviously, specifics are between very and extremely complicated, but that's the broad idea. So essentially, the idea is that instead of trusting in more like legal contracts, the trust is put into software and kind of security of protocols, and everything else kind of happens by itself. So yeah, what exists kind of without trusted execution environments is storage exists in pretty good ways. Obviously, it always can be better. I will get into how. Retrieval is really hard, and this is kind of like CDN style thing where it is really, well, I mean, it is basically been proven that it's not possible to kind of trust two Byzantine parties telling you that a retrieval of data has happened. With compute, there are some networks, but they are also kind of very best effort. So it's like nothing really solid. It's like a couple that already exist, kind of using trusted execution environments that are pretty good, but they're also not really coupled to storage or retrieval, so doesn't really form a good primitive. Now, so the kind of core thing we're looking for in these is they had this really powerful concept of now we don't really only have to trust. Like if I'm a participant in the network, I can only trust my software and my computer. And I don't trust anyone else. But now with TEs, I can trust something that someone else is running on their computer. And it is a really powerful concept. And so it's kind of getting some broader themes of how that is applicable. And so one major thing is it's like possible to prove way more about what other people's computers are doing. Obviously, improving data confidentiality, that's like the more obvious one. And then also it gives a much better job to run compute jobs on other people's computers in a way that's trustable, because like the providers cannot tamper with that computation. And so I'll get into all of them, starting with the compute on trusted providers, which is kind of the simple case. Kind of already a few companies exist implementing that in decentralized networks. So this roughly is gonna get something to run, start a VM container, whatever, give it some memory, network, cores, storage, all this stuff, and then get paid for used resources. Now, there are challenges. So network storage are more or less simple. And like the challenges are mostly around resource use has to be measured for everything that is rented and paid for, because the kind of difference in those networks is that there is no legal contract between the client and the provider. And it can be really hard to kind of take a provider to court or get a refund, or kind of do anything as a client to have a way to enforce getting all the resources that have been paid for. So kind of everything has to be based on very limited trust. And so network storage is kind of easy because they can be mostly measured through a proxy confidential compute VM. And then memory is generally also kind of easy. And I will add one thing. So if there are any questions, feel free to chime in chat, or just raise a hand, and I should be able to see you. I want to keep this kind of open and with back and forth. But yeah, memory is also kind of easy. One tricky thing is memory speed matters, and providers can be something quite Byzantine in just like underclock everything just to a maximum degree, to like save on power costs and anything. I see a hand. Mike.
Just to note that these are indeed difficult problems. Nathaniel, who I'm not sure is on call at the moment, and I actually put together some patents while we were at Red Hat around ways of being able to make estimates that you can trust to some degree as a client, and ways of doing that, which I'm happy to talk about on another occasion if that's something that's of interest to you or anyone else.
Yeah, amazing. But yeah, it's like all of the things, like, course, like exact number of cycles executed, something approximating the amount of work needs to be known,
Yeah,
and then
it was
time.
ways of trying to get things you could trust, which were difficult uh, for the host to fake, basically. So anyway, it's
Oh
fun
yeah,
stuff.
yeah. It's like short version performance characteristics do matter here a lot. But yeah, moving on. So that was like the compute. This is already, I believe, already there are 2 or 3 different networks that are working with, at least at some level, with the common competition compute runtimes, or like platforms. So like SNP and TDX is definitely not uncommon to see. But yeah, there is much more. So growing data confidentiality, this really applies mostly to storage networks specifically. And so the way they work today is generally providers store whatever they are sent by clients. And this is problematic in multiple ways. So yeah, like main one would be providers can see the client store. I see a hand from Alec.
Yeah, I'm just curious about your first bullet point. You say that encryption is often not enough. I'd be curious to hear you elaborate on that, but you can get to it
Oh
when
yeah, yeah. So So generally, like clients can encrypt their data, and they do most of the time, unless it's like a public data set that is meant to be public, but it is most often not the case. And so there are certain cases, like depending on your kind of regulation, like SOC 2, HIPAA, and GDPR have very different requirements, and often it's not enough that data is encrypted if some arbitrary party with no legal contracts can read that. And so there does need to be a way stronger ACL system that kind of makes it impossible for the provider, that like the entity that is storing the data, to have any kind of access to the bytes, even if encrypted. And this is something that could be fairly easily done with ACLs. With computational compute. VMs acting as a proxy to storage, because then the VM can run a piece of software that is only able to establish secure communication with the client, who has the right to read and write that storage. And the secure VM, I believe I have next slide. No. Yeah, so yeah, the theory of this slide is right now the data is kind of sitting on providers. It's a very best effort. It's not possible to prove deletion. This is kind of bad, but with these, it is now in theory possible that if there is a TE that is the only thing authorized to really talk to storage, so hard drives and VMEs and VM hard drives with confidential compute capabilities, in theory, it's really possible to build a system where only the client has the right to read and write to the provider storage, and the provider, the only thing they can do is just allocate the space, and the hard drives would refuse to give them their data. And yeah, I think this is a fairly powerful primitive, especially for storage networks. And honestly, I also believe most of the pieces for that more or less exist today. The other really powerful thing this allows is proving data deletion, which kind of without trusted hardware is just kind of ridiculous concept to like even propose. Like you cannot possibly prove that data has been deleted, but here, if you're going through trusted hardware, you as a client can actually know that that data is gone from that hard drive, and you can also have some pretty good level of assurance that the data has not been copied anywhere, because in theory the provider couldn't possibly access the bytes in the storage. And there are like many reasons for that. Mainly, some clients really don't want their data, even if encrypted multiple times, to be ever read. And there are also some regulations, I think mainly GDPR, that really do require data to be removed when it's asked to be removed. So I see another hand, Alec.
You just answered my question. I was just thinking of at the simplest level. If I create a key inside of a T and I use that to encrypt data before I write storage external to the T, the storage has encrypted data, but it's of no use to anyone unless I leak the key. If I then destroy that key within the T and the T goes away, that key is gone forever, and therefore the data stored are irretrievable forever.
Yeah, I don't think
I didn't
GDPR
realize
lawyers would agree.
is that, yeah, if there are regulations that say, yeah, we're scared, we know you said you shredded the key, but what if the key unshreds itself and leaks? That I get. Okay.
Yeah, it's like purely regulation. Like working in kind of the cryptocurrency space, I am very familiar with how crypto works. I know it cannot be broken, but regulations say but what if? And this is this kind of, if it says it needs to be removed and your client say it has to be removed, there needs to be a way to kind of assure that. I also see a hand from Mike.
Yeah. So it's a question of who needs to know that it's been removed. In that case, I think I agree, because you need to proving that a key has been deleted is no easier than proving that a stored piece of data has been deleted, because you're trying to prove the same thing, basically. Um, so unless you have a way of doing that, and I can think of at least one mechanism that's probably patentable that would allow you to do that, so I won't mention it on the call, then it doesn't make much sense. And even if you're using a TE, to proving that the TE has been deleted, unless you can prove that the key was never exported from it, doesn't really buy you anything, I don't think. So
Yeah, like here, like all of everything hinges on the TE not being tampered with, obviously. And like if the TE software is correct, then the software in the TE should prevent the key from being ever leaked. And like this is the obvious assumption here. And yeah, I will go a bit into the assumptions about the security in a second. So yeah, going next. So yeah, ICLs are also a very big theme. Generally, clients oftentimes just store data and then they give access to other parties to read that data. This is generally true with like everything like machine learning data sets. I guess everything that is a data set, very often we have a client doing the storage and then very different parties wanting to retrieve the data set. And and the clients may not want everyone on the internet to be able to get the data, only the authorized parties. And now in a decentralized system, there's really no good way to implement ACL other than like maybe cryptographic ACLs. And there are some good constructions, but now again, there are clients who are not satisfied with good cryptographic constructions. They need those bytes to actually never leave storage unless they are leaving it to an authorized party. So yeah, this is again where T's can shine, and in general, like the storage can the client can authorize the retriever to be able to go to the provider who hosts the secure enclave, which is able to verify that okay, this person has the right to retrieve the data, and then pull the data from the secure storage and send it to the retriever. And the other thing that happens in those storage networks is there are proofs about the data stored being computed. Those are generally ZK snarks, which is zero knowledge distinct arguments of knowledge or something like that. And those are kind of ways to compute numerical proofs into very tiny proofs, which actually do not leak any knowledge about what was input into the proof. So now it's even possible to compute proofs that the data is stored correctly without exposing any of the data to the provider. And this is maybe like a bit into the weeds, but also really important for some clients. And data deletion, already touched on that, but generally it could be a really powerful primitive. And yeah, then the attestation in decentralized networks. So really, it's just a proving system, kind of like ZK snarks. And so the way those proving systems works is there is kind of one function which makes it possible to create a proof. And this generally has the kind of two inputs, so public information and private information, and then a verify, which takes the attestation or proof and the public information and returns whether that's valid or not. And so one example of what is kind of this proof is, let's say attestation says that private data is some raw data, let's say 1 gigabyte file, and public data is just a hash of the data, like let's say SHA-2 of the data. And the test would say, okay, this data hashes to this hash. This is the attestation that says this is the case. And you couldn't possibly create an attestation that say this data maps to this wrong hash, because the attest function would fail. And then the verify function just takes the, in this example, would take the hash of the data and the attestation, and then would say true or false. And now if it is true, it means that the person who created this attestation had the raw 1 gigabyte file. And the attestation couldn't be created without it. And now it's possible to put really anything in the public-private fields, and you can prove basically any arbitrary thing about the data. And this is what ZK snarks allow you to do, but they are thousands of times slower than running a native CPU. And so might seem like a big deal for most things, but there are some things that need to be proven that, there's a difference between hosting one server and 1,000. It's a pretty big difference. So yeah, the main challenge in the space is really no one understands the security of secure enclaves, and most people are quite pessimistic about it. So like talking to most engineers in the space is you can start a conversation, and the first response is, oh no, I don't want to touch this because it's been broken over and over. And generally there's a whole bunch of time sunk into explaining it to everyone that's like, oh, well, it's not as bad. And generally people do acknowledge that there is quite a bit of value. But yeah, so there's like a big confidence problem. And so like one thing to mitigate that is to have more like clear assumptions. So it's like the assumption of like there is a finite amount where things can and will be broken. And there's also the kind of thing where there are actors here that have to be ultimately trusted, but kind of those same actors have to be ultimately trusted for just anything else. Like, there aren't that many companies building CPUs, let's say, and everyone uses them, so they better be trusted. So yeah, there are mitigations. So just don't put too much trust in a single VM. So like don't have like $1 billion secret in a VM that can be run by anyone on the internet. So just terrible idea. Then yeah, just avoid sharing secrets, and or like, just avoid putting global very important secrets. Just, don't make a thing that everyone can run. You're like $1 billion target, because someone will eventually be motivated to break it, and they might, or they might not, and that is not clear to developers. So yeah, there's also kind of the option of open sourcing parts of like the very critical parts that in theory shouldn't be breakable. So maybe open sourcing some critical parts of the firmware or even hardware. It doesn't even have to be everything, just kind of the things that establish the root of trust. But yeah, so yeah, going into the use cases of attestations, kind of having the why isn't there much more enthusiasm out of the way? Yeah, how are those attestations useful? So first, for really large computations, there are some limited ways in new research that allow proving larger computations more efficiently, but it's broadly still not even close to native CPU speed, and more than likely will not ever be. Maybe for some really specific proof types, but in general, being able to compute at almost native speed and then create attestations, which are essentially just a proof in this context, is really powerful. And so, yeah, like one example we have is proof of data integrity, where storage providers can be asked by their clients to create an attestation which proves that they have access to every single last bit of their data and it's not corrupted. And this can be done just, kind of like it's like known as data scrubbing in like most file system areas. And this is a thing that is kind of important for more enterprise users, where they're not happy that they have 99.9999 something 9% of the data. They also care about the longer tail of nines, or like they actually want 100% of their bits to be there, and they want the proof of that every week. It's utterly not possible to do without these while having these storage be efficient. There are workarounds, but tangential. And like obviously it's possible to implement something as a hybrid of proof and compute. So it's possible to do queries over data sets in a way that the query results are proven. Like you could literally just run SQLite instead of the VM in a conventional compute VM, and that would already be just a magical self-proving results thing. Similar with retrieval. Retrieval is one of those things that is not really possible to prove, but it is possible if the two sides that are exchanging the data are running the code that is possible to that can create attestations on both sides. And yeah, like you can actually prove data exchange this way, which is also a thing that's not possible to prove, and it's been formally proven to be impossible to prove without assuming a secure execution environment. Kind of similar to retrieval, just proving this access parameters. So just being able to pay for access speed, bandwidth, and so on. And there are some later use cases. There is actually one company, at least I'm aware of, that is actually already built a thing around this, but it's kind of limited, but not having access to start. So, and I believe they already use SNP or TDX or both. So yeah, but this again is really limited by not having certainty on the security bound, and yeah, it's kind of unfortunate. Like the security bound is the word used in the decentralized world to describe of how much value is this primitive able to secure without being broken, or like how much money would a motivated attacker need to spend to break this primitive. And this is not a number that is really known in when evaluating these. So yeah, the things that are needed is some kind of runtime, and this may or may not exist already. I've really only done like 3 weeks of deeper research into TEs. Maybe the fact that it took me 3 weeks and I still don't know is also a good feedback to create maybe like some more ecosystem overview documentation where it will be much easier to find this. But yeah, the short version is the runtime that's needed here is something where it is really easy to ship code that creates those proofs, attestations in really light virtual machines that are very, very locked down. So like super secure. I see a hand mic.
Yeah, so that is exactly what we designed NARCs to do. If you look for narcs.io, it's one of the CCC projects. It's currently quiescent. No one's working on it, but it uses WebAssembly to provide you with a very, very light.
Yeah. That is in the next slide.
Oh, that's very nice to hear. So I'm the co-founder, and Nathaniel, if he's back, is the other co-founder of that. So okay, cool. I'll shut up and let you carry on.
Yeah, but that's kind of, there needs to be this runtime. Now, what it needs to do is just run really simple components. It's a general proof primitives are very, very simple, and it's kind of rare to see proving schemes where whatever is proven is extremely complicated. Persistent storage isn't even necessary, and yeah, the one thing that's needed oftentimes is really high throughput, kind of having access to HPC primitives and churning data for data really fast, because often it will be kind of database queries or just going through large data sets. And in general, that means like 100 gigabit, 400 gigabit kind of data rates. And like at those speeds, it kind of would be really nice to have even maybe easy access to RDMA like primitives to get access to data. But even without that, like it probably cannot be WebAssembly as much as I could. But so yeah, this really looks like function runtime maybe, and the like rough architecture here is there's some function that runs on the provider that has access to data on the provider that can ingest a lot of it and just spew out a very tiny attestation at the end. So yeah, it exists. As far as I am aware, it's only Wasn't-Time, and Wasn't-Time already actually worked on a couple projects involving it, and it's really nice. It's extremely fast, but I don't think it can go that fast. Like kind of the difference between writing code in Rust and hoping it go fast versus writing AVX512 assembly, having it go really, really fast. And
yeah, so we designed NARCs to allow you to swap out that layer if you wanted to, as we use Wasn't-Time as the main, but partly because it allowed us to make the highest assurances in terms of security. But it should be possible to have a different execution layer if you want to do that. So it is possible.
Okay, yeah, so that might be a really good candidate then. But yeah, obviously Cocoa maybe stacked with some functions as a service, like OpenFast or something in this theme. And possibly I'm also missing things, but yeah, like if nothing here can work, then it shouldn't be too wild to create something more custom, because it really should be like a really locked down OVMF and like Linux, maybe not even, because the computation is kind of really just reading data from some source and then outputting the result. Like it doesn't even need. I mean, it would be nice if it could run in VM user space, but maybe not necessary. But yeah, so some runtime. Then there's kind of this blockchain related part often appears. So essentially just PKY on chain and like kind of just code to verify attestations, but kind of in the blockchain world. So kind of rewriting what kind of already exists outside of it into that kind of weird realm of having weird limitations on how things are done, but shouldn't be too hard. It just no one asterisk. One group exists that kind of did it, but yeah, there's some work to be done on that front, and then yeah, so there's like this group, Marlin, with their Oyster project that seem to have done most of the work already. And yeah, I'm not really aware of many others. There are some projects that seem vaguely interested in at least SMP and TDX in ways that would also require this work. So it's probably already happening somewhere in the shadows. So yeah, the challenges, what's also needed. So I was kind of surprised to learn that confusion compute work even exists a couple of months ago, because I'm kind of working with like the bleeding edge of server hardware, and like I heard the term bounce around but never looked into it. And when I discovered it, it was kind of mind blowing. It was like, oh, this exists for years and I've never known. If I don't know, then most people don't know.
Yeah, our job is to try and change that, and we'd love to have more suggestions about how to do that. So please work with us on that.
Yeah, I see 2 hands from Stefan and from Dan. Dan was first, I think.
Great talk so far. Just a heads up for people who are coming down in the last few minutes. If you've got questions, make sure you get them in for Magic here.
Okay, yeah, this is usually the last slide.
Okay, great. As far as verifying attestations on blockchain, I'm dropping a link in the chat of we had a consensus mechanism in a project I did several years ago that relied on an enclave, and in order to make sure that that was verifiable across the chain, and sort of in the, for people who haven't worked on those, there you need to be able to always kind of like replay transactions from the start of time and forward, and keys will expire and be rotated and stuff. So some of the things that we did to make that functional in those constraints was to like kind of commit some of those artifacts onto the chain, so that at any point in time you could verify an attestation on there.
Yeah, that is very useful. Also, Stefan.
Yeah. Hey, first of all, thanks for letting Magic present. Magic, great job. As maybe most of you know, or maybe not, we are part of the Decentralized Storage Alliance, right? Started by Falcon and Protocol Labs. Our goal is exactly to what you were just describing. Magic is like, hey, I didn't know about confidential computing until like a couple of months either, but we can help put it on the market. We can help promote it. Also, we're seeing like more in the last couple of months, more focus from some of the decentralized computing networks, focusing now on TE specifically to go after smart agents and this whole AI wave. So I think we can collaborate there by demonstrating how a decentralized storage layer plus decentralized compute that supports TE, and how enterprises can take advantage now of these new technologies in a secure way.
Please get in touch with me and let's discuss how to do that. This is Mike Bursell. Okay, exactly. Very interesting. Thank you.
Yeah, so kind of wrapping up, also hackers would be really welcome. This ecosystem is super open, and yeah, if there is Anyone, any questions? Maybe now, maybe not now if there's other things to be addressed, but yeah, and this is my email. So if there are any questions, feel free to mail that. Maybe there.